And we're going to be talking about radiocarbon dating in both archaeology and ecology. And the two examples that we're going to talk about are Genghis Khan. I'll talk about the archaeology side, and then Stewart is going to talk about the Australian lungfish. So I'll just start with a quick rundown of what is radiocarbon dating and how do we actually do it. And then I'll talk about dating in archaeology, which is probably the kind of application of radiocarbon dating that you are likely to be more familiar with. And then Stewart will talk about how we can use the technique to age animals for use in ecology. So maybe a slightly different take on radiocarbon that you might be aware of. So radiocarbon dating is used over the last 50,000 years, and that is in the very end of the Quaternary period here. So it's quite a recent area, but it's a time period where we have a huge amount happening in archaeology and a huge amount happening that is of huge interest in the paleo environment as well. Now, there's a lot of different dating techniques that we can use to work out how old things are in this time period. So we've got things like amino acid racemization, dendrochronology, this is counting tree rings, a whole range of techniques which are based on the decay of uranium. So uranium series dating, and then very strange techniques called electron spin resonance and optically stimulated luminescence. And tetrachronology is based on volcanism, so using volcanic explosions to work out chronologies. But the most widely used dating technique over these last 50,000 years is radiocarbon dating. And that is what we're going to be talking about today. So radiocarbon dating was developed initially around the time of the Second World War. And in fact, a lot of the people involved in the development of the method were also involved in the Manhattan Project. So it started off in about 1936, where someone called Sergei Korf predicted that carbon-14 should be produced in the atmosphere, but he wasn't able to measure it. In 1940, so just 4 years later, two guys called Martin Kamen and Sam Rubin measured carbon-14. Now, there's hardly any carbon-14 in the atmosphere. So they actually had to irradiate a sample to get enough carbon-14 to actually detect it. But this was the first time that they actually showed that this thing called carbon-14 existed. And by 1946, someone called Willard Libby came up with the idea and published the idea that maybe perhaps we would be able to use carbon-14 as the basis of a dating technique. And by 1949, he and his student Ernest Anderson had been able to develop a piece of equipment which could actually measure natural abundances of carbon-14. And also at the same time, they were able to measure the first ages of ancient samples. And they showed that, yes, we could use this carbon-14 to get the age of a sample in the past. And the significance of this finding was realized very, very rapidly. So that by 1960, so yeah, just 11 years later, Willard Libby won the Nobel Prize for Chemistry for the development of radiocarbon dating. And the significance, I think, is really nicely summed up by a quote from Libby's Nobel lecture that was given in 1960. So he said, "You read statements in books that such and such a society or archaeological site is 20,000 years old. We learned rather abruptly that these numbers, these ancient ages, are not known accurately. In fact, it is about the time of the first dynasty in Egypt that we have the first historical date if any real certainty has been established." So before the 1950s, it was very, very, very difficult to work out how old things were. And this is particularly the case in Australia. So until the 1960s or the late 1950s, people thought that people had only arrived in Australia a few thousand years ago, maximum. With the development of radiocarbon, this is pushed back to 10,000, 20,000, 30,000. And we now know, in fact, that people arrived in Australia probably before 50,000 years ago. So so beyond the limit of the radiocarbon method. And this is now widely known as the radiocarbon revolution within the fields of archaeology and also paleoscience in general. Okay, so how does radiocarbon actually work? To understand this, we have to understand that that an element can have multiple different forms, and these forms are called isotopes. So an isotope has the same number of protons, but a different number of neutrons in its nucleus. So the number of protons defines what an element is. So all atoms of carbon have got 6 neutrons in their nucleus, but you can have different weights of carbon. So carbon-12 has got 6 protons and 6 neutrons in it. So it has a mass of 12. And this is the most abundant isotope of carbon in the atmosphere today. So about 99% of the carbon is carbon-12. And it's stable. Carbon-13, as you might realize from the name, is a bit heavier. 6 protons, but 7 neutrons in the nucleus. And that's about 1% of the carbon in the atmosphere today. Now carbon-14 is heavier again, and now it's got so heavy that it's unstable, it's radioactive. And it has 6 protons and 8 neutrons in the nucleus. And you can see from this crazy number up here, about 1 times 10 to the minus 10% of the carbon in the atmosphere today is carbon-14. So it's very, very rare. And yeah, we're made of carbon and we don't think of ourselves as being radioactive. So it's a very, very rare isotope in the environment. And as I said, carbon-14 is radioactive, so it decays radioactively. And radiocarbon decays by a process called beta decay, and this is an emission of an electron from the nucleus. Okay, and carbon-14 decays to nitrogen-14, which is the most abundant and stable isotope of nitrogen. So to understand this a little bit more, you can think of a neutron, which is a neutral particle, as being composed of a proton, which is a positive particle, and an electron, which is the negative one. If we get rid of 1 electron from a neutron, we're left with a proton. So we've increased the number of protons in the nucleus, so we've changed what element it is, and it's now become nitrogen, which has got 7 protons in the nucleus. Okay. So radioactive decay is an absolutely amazing thing to work in, to use as a kind of clock for the past. Because if you heat up something or you submit it to huge pressure, you're not going to change the rate of decay. So radioactive decay will always look something like this. So we have this really nice exponential decay curve. And it's defined by what we call the half-life, which is the time taken for half of those carbon-14 atoms in a sample to decay. And for radiocarbon, this is 5,730 years. So you can see after just under 6,000 years, we've got 50% of the carbon-14 atoms in a sample have decayed. And then after just under 12,000 years, we're down to 25%. Now I'm just going to exit my PowerPoint because there is a really nice little movie of what this would look like. Let me see if I can start that again. No, I can't. Okay, so this little display up here, we can see our exponential decay curve down here. And in this box up here, you can think of this as a sample of carbon, and the little yellow spots are your carbon-14 atoms. And we'll just wait for it to finish and then start again, and you'll see why we can only date to 50,000 years. Okay, with radiocarbon. Okay, so right at the start, you can see that there's lots and lots and lots of carbon-14 atoms, and lots of them are decaying. So we have this really rapid decrease at the beginning, up to about 10,000 years. And by the time we get to about 20,000 years, we don't really have that many carbon-14 atoms left. So we have, a much slower rate of change. And then by the time we get to 50,000 years, there are so few carbon-14 atoms that we can't actually distinguish the carbon-14 atoms in the sample from the carbon-14 atoms that we would get from measuring a blank in our equipment. Okay, so yes, by 50,000 years, there's hardly any carbon-14 atoms left and a very, very slow rate of change. Okay. Come back here. Right, so most carbon-14 is produced naturally in the upper atmosphere. Stuart's going to talk about a slightly different way of producing carbon-14, but generally in the past, most of the carbon-14 has been produced in the upper atmosphere, where cosmic rays interact with the upper atmosphere, and they produce neutrons. And those neutrons will react with nitrogen-14, to produce carbon-14 and a proton. And then that carbon-14 is very rapidly oxidized to carbon dioxide, which can then be taken up into the food chain by photosynthesis. And eventually, when we eat our lovely picnic, we will incorporate carbon-14 into ourselves. And we would say that this, the amount of carbon-14 in plants and in animals and in the atmosphere exists in what we'd say call a dynamic equilibrium. So if you were to measure a part of your body which turns over rapidly or is renewed very frequently, like your skin or your blood, you're going to have about the same amount of carbon-14 or the same ratio of carbon-14 to carbon-12 as there is in the atmosphere. But when you die, you're no longer taking in carbon from your diet. So you will start to see this decay of carbon-14 to carbon-12. And then after you've been buried for 50,000 years, you no longer have a detectable level of carbon-14 in your bones, which is probably, or teeth, which is probably all that's left after 50,000 years. So what can we measure? Well, we can measure carbon-14 in anything which contains carbon. In terms of dating processes, most of the time we're talking about living organisms. So tree rings are absolutely beautiful things to date. We have speleothems and corals, so carbonate formations. We can do things like jaws and teeth. Occasionally you get these amazing finds. This is a mummy of a mammoth from Siberia, a baby mammoth from Siberia. We can date shells, and these are shells of foraminifera from ocean sediments, and we absolutely love to date seeds. Okay, so how do we actually do it? Well, the first thing we have to do is select a sample, and this is I would say, as an archaeologist, the most important part of the whole process. You really need to find the best possible samples you can within an archaeological kind of question. So this bone here is one that I dated in my PhD, and it's a bone, I think actually it's of a red deer, and you can see these marks across here. So these diagonal marks were made by a stone tool in the process of butchering the animal. This bone was found in deposits where the stone tools that are associated it would suggest that some of the earliest modern humans in Spain. So we know by dating this bone here, we're getting a very, very well associated age of those early modern humans in Spain. And it's around 42,000 years old. Once we've sampled, taken our sample, which is normally, say for bone, we're looking at less than a gram. So it is destructive, but it's not very, very destructive. We then need to clean the sample, because you can imagine if your bone or your piece of charcoal or your wood has been buried for 40,000 years, it's going to have a huge amount of other big stuff in it. And that stuff might well contain carbon. So we go through a cleaning or a pre-treatment process. We then need to convert it into graphite. So this is converting it into a form where we can measure the carbon-14 to carbon-12 ratio. This is a piece of equipment that Stewart built, and it's a really good, really fun process. We use lots and lots of liquid nitrogen and lots of dry ice and vacuum pumps. This is quite a fun process. And that's what we're left with at the end here. So these are our cathodes or targets, and that little black spot in there is where the graphite is. So from about 1 gram of bone, we're left at the end with less than 1 milligram of carbon, pure carbon, which goes into the accelerator mass spectrometer. So you can see, again, Stuart's got another picture of the AMS behind him on his background. This is a very large piece of equipment, which allows us to actually count the individual carbon-14 atoms. But yeah, Stewart will, I think, is going to try to show it to you in live time if you're interested, right at the end of the presentation, if you're interested to see this piece of equipment. They're relatively rare pieces of equipment. There are currently 3 radiocarbon dating labs in Australia, which have got one of these. There's one in New Zealand. Yeah, so they're kind of national resources. And after measuring this carbon-14 to carbon-12 ratio, we're left with the radiocarbonate. Now we measure this as, the unit is BP, which means before present in radiocarbon speak is 1950. So this is when Willard Libby started to measure. But the important thing to know is that it is not equivalent to a calendar age. And that is because the amount of carbon-14 in the atmosphere has changed over time. And this was realized very soon after Willard presented his first dates. And it varies mainly, there's a number of different reasons, but the main reason it changes is because of fluctuation in the amount of cosmic rays received in the upper atmosphere. So, and again, there's lots of reasons why these change. It might be due to changes in what's happening on the Earth's surface, on the sun's surface and the sun activity. And another major change is because the Earth's magnetic field strengthens and weakens over time. And cosmic rays are magnetic. So if you're changing the magnetic field of the Earth, then you will change how many cosmic rays can actually enter the atmosphere. Yeah. So to get around this, we have a calibration curve, and was it about 1.5 weeks ago, the most recent calibration curve was published. This is in Cal 20. And I have put a picture of Paula Riemer here because I don't want to give the impression that radiocarbon is dominated by black and white men. Paula Riemer has led the working group which develops these internationally accepted calibration curves for the last 20 years now. And you can see the calibration curve in this blue wiggly line here. So you can see that it's got very short-term wiggles, it's got some longer-term kind of deflections, and it tells us a lot about changes in the Earth's magnetic field and the changes in sun activity, which is another way radiocarbon could potentially be used. Now it's developed by dating things where we know how old they are already. So for about the last 14,000 years, we've got tree rings. So you can count, we all know that we can count back tree rings, and we could radiocarbon date each one of those tree rings. And because we know how old that tree was, and once a tree ring has been laid down, it no longer turns over or changes. So if you radiocarbon date your tree ring, you'll be measuring the carbon-14 to carbon-12 ratio of the year that it was produced. Okay, but if you think that you can do that across a single tree, that would only go for a few hundred years. But you can see in this piece of wood here that the ring widths vary quite a lot, and you can use these variations in ring widths to match different pieces of wood together. So we actually have a master chronology now in Europe, which goes back to 14,000 years. So we have a tree ring and radiocarbon record going back 14,000 years to build this calibration curve. Beyond that period, it becomes much more difficult to get good kind of calibration records for radiocarbon. So beyond about this point here, the curve is not quite so secure, and it changes, which is why it needs to be routinely updated every few years. At the moment, this part of the curve is based on things like lake records. So this is a core going through a lake, and each one of these dark and light bands represents a year. And numerous poor students and postdocs have had to count those. They go back to beyond 50,000 years. And we get lots of things like leaves and seeds preserved in this lake record. It's a very unique record. It's Lake Suigetsu in Japan, and it's really the only one that we have that goes back so far and so beautifully, as we'd say, laminated. So we also have things like speleothems. So these are your carbonate concretions that you get in caves. So this is a cave in China called Hulu. And we have, radiocarbon records through these speleothems, which are then dated with another method called uranium series dating in a similar way to, there's also corals in there as well. Okay, so that finishes how we would do radiocarbon dating. So when we apply it to archaeology, I think a lot of my students tend to think that dating is just getting a number. It's quite boring, but it can tell us a huge amount about what people were doing, why they were doing it, how they were doing it. So it informs process. So I think that chronology can be used to reveal two things. The first one is the order of events. So this is the very simple thing. If we want to know, for example, did modern humans, or did the arrival of humans in Australia have an effect on the megafauna and the extinction of the megafauna in Australia? So we had these huge animals. If anybody doesn't know, this one here on this image here is a diprotodon, or a kind of like a giant wombat. And people have argued for a very long time, and they continue to argue why these went extinct. If we can accurately and precisely date when megafauna went extinct and when people arrived, we can say, well, if people arrived after the megafauna went extinct, they can't have played any role in what was going on. But if they arrived before the extinction date, then we would say, well, there was a period of coexistence and people could have had a role in the extinction of those megafauna. And that's when we come to the second thing that dating can reveal, and that's the speed of change. So you might think that people will have had a different impact on the extinction of megafauna if they arrived a very short time before the extinction date, or if they'd been around maybe 10 or 20,000 years before the megafauna went extinct. That period of coexistence and the length of the period of coexistence can give you an indicator of what kind of role people might have had in that process. And the speed of change is also really interesting when we start to think about kind of more traditional archaeology. So this is a long barrow. It's a kind of burial monument that was used by people in the Neolithic. So these are the first farmers in southern England. And radiocarbon has recently shown that these were used only for a very short period of time. So that tells us that the people who closed up, so quite often we find that the openings to these burial mounds were closed. The people who closed that monument would have known the people who built the monument. They would have known who all of those bones in that burial mound relate to. It's not like they're closing up and blocking out what we might have previously thought of as a faceless ancestor. So speed of change is almost, I think, almost more interesting than the order of events. So I'm just going to give you a quick introduction to some work that we've collaborated very recently on about Genghis Khan. And I chose this example because I thought most people, even if you come from more of an earth sciences interest, are going to probably have heard of Genghis Khan. So he was the kind of ruler of kind of this whole area in the 1200s AD. So it was one of the biggest empires ever in terms of area, and he had quite a reputation for fathering an awful lot of children as well, had many, many wives, was an extremely, extremely powerful ruler. Now, we were asked by one of our collaborators in the College of Asia and the Pacific, so Jack Fenner, who was working with some Mongolian and some Japanese archaeologists at a site called Avraga. And they wanted to know, was this site the winter residence, or could it have been the winter residence of Genghis Khan? So there was a bit of historic and linguistic evidence that was suggestive that this site could have been the winter residence or Urdu. But it's quite an interesting site. So it consists of the remains of wooden and earth-packed structures. Now, this is quite unusual. I don't know if you've probably seen pictures of yurts, so the traditional nomadic tents. They're very substantial tents, but tents of the nomads in Mongolia. So it's quite unusual in the archaeological record to come across kind of wooden buildings. But there were no high status goods. So there were none of your beautiful gold jewelry or what you might associate with what Genghis Khan probably had in his pockets or on his clothes. But on top of these wooden and earth-packed structures in some parts of the sites, there was a platform that was used for ritual or commemorative events after this initial settlement, which suggests that this probably was quite an important site. Okay, Genghis Khan only lived for quite a short period, so 65 years, quite a long time ago. So between 1162 and 1227. If we were to simulate a radiocarbon date from 1200 AD and we calibrate it, we get a very, very wide possible age. So to take you through this little plot here, this blue line here is your calibration curve. So it's just a little snippet of that curve that I showed you earlier. And this red probability distribution here is your radiocarbon age. And you can see, so your uncalibrated date that we get from our accelerator mass spectrometer. So the most probable age is here. If you draw a line across to the calibration curve and you drop down from your calibration curve, we can see that most likely, most of the probability of the age is around here. But you do have, because your curve is very, very wobbly, we do have some probability that whatever we had dated here, say a bone, could have been from 1050 to about 1100. Okay, so if we were to just get one radiocarbon date from this site, it's not really going to tell us very much, and we're not going to be able to say with any security whether this site was occupied during the life of Genghis Khan. So what we do is we use a type of statistics called Bayesian statistics. I'm not going to go into it in any kind of detail, don't worry. But I just want you to realize that it's different kind of statistics completely to the kind of classical statistics that you're probably useful. So things like your average and your standard deviation are what we call classical statistics. Bayesian statistics are very, very different because they allow you to incorporate your prior beliefs. So what do we already know about the chronology of a site to get an answer? So what we can say is we combine the standardized likelihood, which is our radiocarbon dates, with our prior beliefs, so that's your archaeology, so we'll go into that in a minute, to get your posterior, or your answer. So what we can think of in this case study that I'm going to give you, which is quite a simple one, is that the site starts. The site starts, and then it continues. So this is where our radiocarbon dates are going to go, and then it will end. So we have a start date, the continuation of it, and then the end date. In the kind of modeling that we use, we would say that this is a phase of activity, and it's bounded by two boundaries, and these boundaries give us an estimate for the start and end date of the phase. These are not radiocarbon dates themselves, they're the result of the statistical analysis of the radiocarbon dates combined with this phase here. So we get, from this site, we dated a whole collection of animal bones that were found in various different pits. So we know that people put these animal bones in those pits. And you can see the very pale distributions here. These are your calibrated radiocarbon dates, and they scatter quite widely, all the way from just over 1,000 to well over 1,200, 1,250 here. When we do the radiocarbon modeling, so this Bayesian modeling, and we put all of our radiocarbon dates in one phase, we get these dark probability distributions here. And you can see that the precision has increased dramatically. So that's because we're incorporating a lot more information about the chronology. And we can see this here is our start date for the site, and this is the end date for the site. And you can see that they all line up very, very closely, and they line up basically entirely within the lifespan of Genghis Khan. So this is this paler distribution from here to here, so 1162 to 1227 here. And they are most likely, in fact, even to be within the reign of Genghis Khan, so this even shorter period here. So we can say from a chronological basis, this site was almost certainly occupied during the reign of Genghis Khan. And if you combine that with the archaeological and the linguistic evidence, it's pointing very, very securely to the fact that this was Genghis Khan's site or his winter residence. And then it becomes very interesting to think about why we don't have any of this kind of high status jewelry or remains of a very wealthy individual. Okay, so I'm going to hand over to Stewart now. And he's going to talk about his lungfish for a completely different, I need to stop sharing. There we go. Okay.
Thanks, Rachel. Thanks for that great introduction on radiocarbon and a really cool example of the Bayesian modeling of Genghis Khan. So I'll share my screen now. Hopefully. Okay, so I'm going to talk about some ecological work that we've done on the threatened species, the Australian lungfish, which you can see down in the bottom picture here. And so the title of this part is, how can we age a protected fish? And we're going to use the atom bomb, of course. So we'll start off, I'm going to just quickly talk about bomb pulse dating, which is an additional part of radiocarbon dating, and then a bit about lungfish and why we're interested in knowing how old they are and how long they live. So Rachel gave us a nice explanation on how carbon-14 is produced in the upper atmosphere. You have these cosmic rays coming in, hitting the nitrogen. But during the early 1950s and early 1960s, atmospheric nuclear weapons tests produced high amounts of neutrons as well into the atmosphere, and they produced an abundance of carbon-14. Here we just kind of see where all of the tests occurred across the globe. Quite a large number of them were in the Marshall Islands in the Central Pacific, tests by the United States and the Soviet Union up here. But what happened is that all of the tests essentially doubled the amount of carbon-14 in the atmosphere. So this graph here shows the delta C14, which is essentially the amount of carbon-14 measured in carbon dioxide in the atmosphere. We have two curves here to look at. The data goes from about 1900 to 1990 or so. But the red curve is from atmospheric carbon in the northern hemisphere, and it goes up to essentially almost doubling the amount of C14, and then the yellow one is in the southern hemisphere. The northern hemisphere is higher because essentially all of the tests were done in the northern hemisphere, and it takes a little while for that CO2 to spread around the globe. Just for completeness on this figure is basically the surface ocean amount of carbon-14. So the surface ocean has a large reservoir of carbon, and there's some old carbon in there. So the amount of carbon in the surface ocean is much lower than in the atmosphere. But because of this testing, and the testing occurred up until 1963 at the Nuclear Test Ban Treaty, and then since then, the amount of carbon-14 has been mixing and decaying away into the carbon biosphere. So because of this, basically this curve of bomb radiocarbon, we call it, that's developed what we call bomb pulse dating. And so we have this distinct curve with a sharp rise up till 1963, and then it's decaying away. And the curve, you can measure the curve anywhere across the globe. And so, as Rachel had mentioned, all living things take up carbon-14 from the atmosphere, either directly via photosynthesis or indirectly as your food. So something that's born or dies between 1955 and today will have this distinct carbon-14 signature. And so one of the items that are often used is carbon-14 bomb pulse dating for forensics, so determining when someone was born, so you can measure the carbon-14 in tooth enamel, and that tells you when the person was born. Or you can look at the islands. So there's some parts of your body that the carbon doesn't turn over from when you're born. Then there's other parts like your blood and hair that have the most recent amount of carbon-14 in them. So we can use them to date. So we're going to try to take advantage of this bomb pulse dating to try to understand the age and life cycle, and trying to understand the population dynamics of the Australian lungfish. So the Australian lungfish basically has a very simple lung system. So as well as gills, so it can breathe underwater and breathe air. It's been around for hundreds of millions of years, 140 million years. Its habitat is increasingly under pressure because it lives in small tributaries and streams in southern Queensland, and building and changing water usage, building dams and things has really impacted its habitat. Traditional fish methods for aging uses what's called nodolith. But these fish are so old they don't actually have this ear stone, but I'll talk about that in a minute. So we have a project that we have been working on for the last few years. We're trying to determine how long the lungfish live, if we can get some information about the environments that they live in. I won't talk about it, but another group that we work with looked at genetic diversity. But here's just a couple of images. Here's quite a large lungfish. And what you can see on here are their scales. And then this is a juvenile lungfish. So the lungfish live in southern Queensland. So in areas in the Brisbane River. And then if you go further up to the Mary River, this is Fraser Island up here in Queensland, and then off of Brisbane as well. Because they're threatened fish, you wouldn't want to kill them anyway. What we did was we just pulled a scale off of each fish. So we collected about 1,500 fish, but we only measured about 120 or 160 of the individuals. And what we found is that they aged anywhere from between 5 years and greater than 70 years old. So the traditional methods, as I started to mention, is looking at a fish otolith. So this redfish here, they're pulling out an ear stone. So that's a calcium carbonate stone in the kind of the auditory canal, or I guess the ear area, ear bone of the fish. Unfortunately, the fish has to be dead in which to remove that ear stone. And this is just a close-up image of one of those ear stones. And what most fish have is you can see these alternating bands. And so they have slower growth and faster growth throughout the year. And you can count those back and tell how old a fish is. The lungfish are so old that, or been around for so long, they don't actually have this calcium carbonate earstone. So this is just a close-up of the fish, and here is one of the scales that you can pull off the fish. So the fish are collected, put up on the boat. They're weighed and measured their length. Some scales are pulled off, and then they slide them back into the river to swim again. So here's just a closer look at some of the scales. So the dark part is the part that you see on the outside that you can actually see on the fish. And then the lighter part is the part closest to the skin of the fish. And this is the part of the scale that's that extends and is kind of growing. So it's kind of almost akin to a large toenail. Before we can measure the samples, we have to do some pre-treatments and mechanical cleaning. So we have to remove this kind of outer layer on the scale, so we're left with this kind of translucent material. And then we slice the samples into sequential slices, and they weigh about 1 to 1.5 milligrams, and we do them about every 0.5 millimeters. As Rachel showed, we have to do our sample processing. So one of the steps that we do is we load the samples into a quartz tube over here on the left, and evacuate all the air out, seal the tube with a torch, bake it at 900 degrees with some copper oxide to make carbon dioxide. And then we use these graphite lines, we call them, to convert the carbon dioxide into graphite, and then Rachel mentioned before where we put them into the sample holders, and then they go into the accelerator mass spectrometer. So what we found is, so here's a picture of one of the scales, and if we measure the carbon-14 from the outer edge of the scale, so the part that's the youngest, we saw the carbon-14 going up and then back down, and then to a kind of a plateau area. So fish tend to grow exponentially, so they grow super fast in the early parts of their lives and then grow really quite slowly. So, and this whole scale, the scale kind of grows from this origin point. The last about centimeter 5 or 6 millimeters was about 50 years. So that's the entire bomb curve in the scale. So basically we're going up the curve and then down to the inside of the scale. And so this is again what the data looks like. So the outside of the scale, we go up to the bomb peak and then back here towards 1950 in what we call the pre-bomb area. So Rachel had mentioned the Bayesian modeling. So that's done in a program developed at Oxford University called OxCal. So we put in a slightly different method, we input that data, and instead of having the calibration curve that Rachel showed, what we have here is our bomb calibration curve. We again have our C14 measurement, so instead of age, we actually just use the amount of C14 that's measured. We tend to do that for samples that are younger than 1950. And then we end up with this probability distribution, as Rachel mentioned. So this particular fish was born between 2002 and 2008. And we can do that for all of the fish. And then, so what we've seen and what I mentioned is that we have quite a number of fish that are, at least 60, 70 years old. We looked at fish from 3 different rivers, the Brisbane River, the Burnett River, and the Mary River. And what we did here was just kind of bin the fish into 5-year windows of their birth date. So the Mary River here, we had fish that were born in the late 1930s, quite a few born in about 1955. But then we had some gaps where no fish were born. And then in the Mary River, since the 1990s, it doesn't look like very many fish were born. In the Burnett River, we also see this kind of gap in the 60s, 70s, and the 80s. But then more recently, we saw good amounts of fish being born. Now the Brisbane River is a little bit different. There was a large dam built, the Wivenhoe Dam, and after that point, it looks like the amount of fish born was pretty consistent. So one of the things that we're going to start looking at is maybe what was happening in the environment during these time periods when it doesn't look like any fish were born. So the lungfish need small little river tributaries and lots of plant material, macrophytes, things like that, in which to lay their eggs. But if you have large floods, which we often have here in Australia, that can wipe out all the plant beds, and there's nowhere for the fish to lay eggs. So if you have a large flood, there may be a few years where you can't actually lay eggs. But it's not so important for this lungfish because they're a very long-lived species, as we've seen, up to 60, 70 years old. So they have plenty of time for developing progeny and stuff. So this is just a kind of a different way of using radiocarbon dating, kind of not in the strict archaeological sense, but in terms of looking at an ecological question. So during this project, what was really quite important is that we developed essentially, it's a destructive to a scale, but not to a fish. And so that's really important if you're looking at threatened or threatened species. We found that they do have very long lifespans. They don't have to successfully have progeny or baby fish every year. They're a complicated fish, but really quite fun to work on. So that's it for the lungfish. There's no one asking any questions, so I'll just go and try to connect my iPad so I can just take you on a quick tour. So I will mute. Oops. Okay, so can you hear me? Yeah. Okay. All right, so we will try to go on a little tour of the lab. So our labs start off, we have a preparation area. It's a bit noisy, I'm sorry. But you can see here, this is where we prepare graphite samples. The samples are loaded into small tubes. And let's see, where is it? So here's the small tubes, and you can see the sample inside. So we load the samples in here, and then each sample goes into one of these reactors where we add the CO2 and the hydrogen and make the graphite. And then after it's made, we walk across the accelerator. So this is our accelerator mass spectrometer. It's noisy because it has lots of vacuum pumps. But basically, we put our samples in there, and then the ions get accelerated. We measure the different isotopes, carbon 12, 13, and 14, in the accelerator. So that was just a quick little tour. If you actually come in person to ANU, please come and visit if you'd like to. And that's about it. So that's all from us.
Yeah. Thank you very much. Okay.
Thank you. And anything else to say, Rachel?
No, not at all. But
okay.
Yeah, if you come to ANU, please come and see us. Okay.
Thank you very much.
Bye.
Bye.